So I will review what we learned in the previous class. So we learned how to handle data hazards in the pipeline, the processor. So I said this is very important topic in the pipeline, the processor. So it is because in the pipeline, the processor, we need to reduce hazard. So why? Because hazard mean the events that waste clock cycles in the pipeline, the process, or any type of processors actually. So if there are many hazards that happens in a certain processor, that means that the performance of a processor can be degraded. So because the clock cycles are wasted, so I frequently mention that in the processor, we assume that one instruction can be executed every cycle. But if a hazard happens, this assumption can be broken. So that means the clock cycles are wasted. So, and then we learned how to handle hazards in the pipeline processor. The first approach is data forwarding. So, and then the second approach is just pipelining store. So data forwarding means that for the R-type instruction, the result is generated in execution cycle. So, but we cannot use this generated result until this result is written back to the register file, because the following instructions read data, so that means the required operands in the register file. But the problem is that the required data is not yet written back to the register file. That is the problem. But this data exists in the pipeline processor, so we can forward this data to the input of ALU. Why? Operands, so required operands are used by ALU. Okay, so and then what is pipeline store? So pipeline, the operation of the pipeline stops temporarily. Okay, actually for certain cycles. So if the formal instruction is load instruction, then the result of the load instruction is generated in memory stage, okay, not EX stage. So in this case, if the very next instruction requires the data from this load instruction cannot be forwarded to this very next instruction, the following instruction. Okay, because the result will be generated at the end of the memory stage. Okay, so in this case, we need to apply pipeline store. Okay, so you need to remember these two approaches. So the first approach is data forwarding, and then the second approach is pipeline stores. Okay. Okay. So and then for this data forwarding, we learned how to build pipeline processor that support data forwarding. Okay, so if we just focused on the input of ALU, because I said that the required data from the formal instruction are forwarded to the inputs of ALU. So you need to remember that, because the ALU requires these operands. And then, so that means that the ALU has three possible paths for these input operands. Okay. The first path is the normal path from this register file. So also you can find that two multiplexers here in front of the inputs of ALU here. So you can find that the first path is the normal path from the output of register file. Okay, so this is the normal path. And then if the data is forwarded from the formal instructions, then there are two possible paths. The first path is this path, so that is the output of the very formal instruction. So for example, add x1, so that means that this add instruction try to store each result to the x1 register, and then the very next instruction receive the result from this add instruction. So in this case, this value should be forwarded from this EX memory pipeline register. Okay, so you can find this forwarding path from the pipeline register memory, EX memory pipeline register here. And then also the data can be forwarded from the write back stage. Okay, so this is the final result from the formal instruction, and then this result will be written back to the register file. Okay, so this is the write back stage. But if you just focus on the location of the next instruction can be here, like so x1, x2, x3, but add instruction is here, like x2, x4, x5, like this. So this x5 should be forwarded to this solve instruction. So you can find that the x2 is being written back to this register file, but this following solve instruction is already located in the EX stage. So here EX stage. So the x2 is being written back to the register file in this register file, but solve is here, so this solve cannot receive this data. So this data, so that means that the result which is being written back to the register file is also forwarded to the input of the ALU. So this ALU received the three possible input data, input operands. So first is from the register file, and then the second is from this write back stage, and then the third possible path is the forwarding path from the memory stage. So output of the EX memory pipeline register. Okay, so this is the required hardware for supporting data forward. So we build our hardware. We build hardware resources, or we build the hardware architecture. And then as you can see, this multiplexer requires selection signals. So that means that we need to generate these selection signals for multiplexers to support data forwarding. So this is the forwarding unit, that is the control unit for data forwarding. And then this forwarding receives the RS1 and RS2 from the which pipeline register? IDEX pipeline register, and receive the RD from the formal instructions. And then the first pass is the output of the EX memory pipeline register. And then another path is the output of the memory write back pipeline register. Okay. And then why? We need to check the RD of the formal instruction and RS1 or RS2 of the following instruction to check the data forwarding. Okay. And then based on this RS1 number and RS2 number of the following instruction and then RD of the former instructions, then forwarding unit generate this forward A and forward B selection signal. Okay. Then this is how the forwarding selection signal is generated by conditions, some several conditions. And then we learned how to generate these selection signals. Okay. So I repeat that. So this is a very important topic. So you need to understand this topic, so data forwarding. And then another approach is pipeline store. So it is because if the former instruction is load instruction, then the result of load instruction is generated in memory stage, and then this map. So the result of the load instruction is generated later than the other R-type instructions. So in this case, if the very next instruction requires the result from this load instruction, then the following instruction cannot receive data from the EX memory pipeline register. So in the previous example, the data can be forwarded from the here to the input of the ALU, but the result of the load instruction is generated from data memory. And then if we just see the timing of the this data memory, then we can say that the result of the load instruction will be generated some time here. So that means that it's the later part of the clock period. Okay. So we cannot use this data if the very next instruction, this sub instruction, is located here. So we need to forward data from this point for the load instruction. Okay, and then in order to support this forwarding, then when the load instruction is here, the following sub instruction, that means that the instruction that requires the result from load instruction should be located here, the EX stage. So when the load instruction is write back stage, then the following instruction should be in the EX stage. So that means that we need to make this pipeline stage empty. Okay. So this is the pipeline store. So you need to understand. So I believe this is a little bit tricky because it's related to the timing of instruction. Okay, so I will explain again for the timing of this load use data hazard. So the load instruction is here, and then in the clock count number 1, the load instruction is fetched from the instruction memory. That means this load instruction is the instruction fetch stage. And then clock count number 2, the load instruction is in the ID stage here. And then actually this is the next instruction. And then this next instruction requires the data from load instruction. So actually the end instruction is here. Okay, because this is the next instruction of the load instruction. So the end instruction is fetched from the instruction memory. So this is the end, this is load. Okay, and then load instruction is located in EX stage at clock cycle number 3. Then this end instruction is located in instruction decode stage. So its end is here. And then at clock cycle number 3, the OR instruction is it's the next instruction of the end instruction. So actually the OR instruction is in the instruction fetch stage. Okay. And then at clock cycle number 4, the load instruction is here. And then if end instruction is in the EX stage, and this end instruction cannot receive the data from load instruction. Okay? Understand? Because the load instruction is reading data from the data memory. So end instruction cannot be in the EX stage. So that means we need to detect this pipeline stall condition by load instruction and the next instruction. When at clock cycle number 3. Why? So if we do not detect this pipeline stall condition at clock cycle number 3, then the end instruction will be here. So we cannot avoid some data this pipeline stall, okay, because the end instruction is already located in the EX stage. So we can know that the first, how to detect data hazard, that means the pipeline stall. How and when to detect the pipeline stall by load instruction. So let's focus on the when. So when load is in EX stage and the following instruction, the next instruction, is in ID stage. So when the load instruction is in the EX stage and the very next instruction is in the ID stage, then we need to detect the load use data hazard. So that means that the pipeline stall situation caused by load instruction. Understand? So you need to understand. Okay. So when the load instruction is here, the end instruction cannot be in the EX stage. So we need to generate the invalid instruction, and then this invalid instruction does nothing. So that means this instruction is a no operation. That's why this instruction is called the NOP. It means the no operation. Okay. So when the load is at clock cycle number 4, load instruction is in the memory stage, and then this end instruction is in the ID stage still, and then this OR instruction is in the instruction fetch stage. Okay. Okay. And then at clock cycle number 5, the load instruction is in the write back stage. And then, this data now can be forwarded to the input of the ALU. Okay. Because the result of the load instruction is generated. So using the data forwarding path we built in the previous class. So this data from the write back to the input of ALU, data is forwarded to the input of the ALU from the write back stage. So at clock cycle number 5, load instruction is in the write back stage, and this end instruction is in the EX stage now, and then OR instruction is in the ID stage. And then also the following instruction, the add instruction, is in the instruction fetch stage. So if we just see this clock cycle, the clock cycle number 5, the load in the write back, and then bubble, that means no operation, is in the memory stage, and is here, ID is here, and then the add is in the instruction fetch stage. Okay, so that means one of the pipeline stages is filled with no operation, that means bubble. So if we just see the pipeline stages, and then for the normal cases, so we can find that every instruction fills every stage of pipelines, right? So the clock cycle is not wasted if every instruction fills every stage of a pipeline, then the clock cycle is not wasted. But if we just focus on the CC5, clock cycle number 5, memory stage is filled with no operation. So that means one cycle is wasted by this load use hazard. Okay, so the first I said, when this load use data hazard is detected. So when, so you need to remember, the load is in the EX stage, and then the next instruction is in the ID stage. And then how can we detect the load use hazard? It's simple, right? How can we detect? The condition is that the former instruction is load instruction. So how can we detect? The control signal is mem read, and RD, destination register of load instruction, is equal to RS1 or RS2 of the next instruction. So I said, when the load instruction is in the EX stage and the next instruction is in the ID stage. So we need to check RD in the which stage? EX stage, and RS1 or RS2 which stage in the which stage? ID stage. Okay. And let's see. That's how to detect load use data hazard. So I explained when to detect load use hazard and how to detect load use hazard. Also, I already explained how to handle load use hazard. So how to handle? The very next instruction. So that means that inst in, so I already explained, inst in ID stalled equal, and then because this instruction in ID is stalled, the next instruction, the following instruction cannot propagate to next stage because the formal instruction stores in ID stage. So that means the instruction in instruction fetch stage also stored. Okay. So propagation is temporarily stopped. And then loop, that means bubble is generated. Okay. So this slide shows how to build this data folding. So not data folding, the load use data out. So that means that the load use hazard detection unit and the load use hazard control unit. So this is the hazard detection unit. And then in the previous slide, I explained that when to detect. So the load is in EX, and then the next instruction, next inst is in ID. And then how to detect. So I explained. And then also required operation. ID stage is stored, instruction fetch stage is stored, and then the loop instruction is generated to the EX stage. Okay, so we need to learn how to store pipelines and then how to generate loop instruction, and then how to store pipelines. How to store. So then how can we propagate instruction from forward stage to the next stage? So this is the D flip-flop, right? So actually I said that pipeline registers are actually D flip-flops, and then the operation of the D flip-flops means that at the rising edge of the clock, this input signal is updated to the output signal. And then if we just disable this update, then we can store pipelines. Do you understand? So normal operation of this D flip-flop is that at the rising edge of the clock, input of the D flip-flop is updated to the output of the D flip-flop. And then if we just disable this update, then we can store pipelines. Because this value is not updated to the output port, output of the D flip-flop. Understand? I hope everyone can understand. So how can you store the pipeline? This is the clock, and then actually there are different kind of D flip-flops. It's like a D flip-flop with the enable signal. So this D flip-flop has the one input port, is a one control port called the enable. So this is the clock, and then this is the D, and then this is Q, the output of the D flip-flop, and then another port is enable. So if the enable is 1, then this D is updated to the Q at the rising edge of the clock. But if the enable signal is 0, then the input signal is not updated to the output signal. Okay, so we can use this D flip-flop with enable signal to build pipeline store. Okay, so actually, so in this slide has the hazard detection unit, and then you can, as you can see, this hazard detection unit received the instruction actually RS1 and RS2, and then what's that? It's a mem read signal. So it is required to get the load instruction. And then you can find this signal. And what is this? This is the RD. And then this RD is from EX stage. As you can see here, okay, RD is here, and then RS1 and RS2 is here. And then as you can see, this hazard detection unit generates the two control signals. So that means that it's a PC write, and then instruction fetch, and then instruction decoding, write signal. So what does that mean? So actually this is equivalent to the enable signal of this D flip-flops with enable signal. Okay, what does that mean? If this instruction fetch ID pipeline register, oh, no, there is no ID here. So instruction fetch and the ID pipeline register write is 1, then this input of this pipeline register is updated to the ID stage. So that means the output of the D flip-flop when at the rising edge of the clock. Okay. Then what is the PC write? So actually the PC also received the next PC signal. So like next PC is here. So at the rising edge of the clock, so it's also D flip-flop. At the rising edge of the flop, the current piece is updated to the next PC. So that means the input of the program counter register. And then this update is controlled by my signal PC write. Okay. So if PC write is 0, then what will happen? So at the rising edge of the clock, the PC is not updated from the next PC value. So current PC is kept because it's not updated. Okay. So, and then if the PC is not updated, the instruction memory will not generate new instruction because this is just the memory and the address is given to the instruction memory. The instruction memory will generate the corresponding instruction that is stored in this memory. Okay, but if the address is not updated, then the same instruction is kept in the instruction fetch stage. So in order to store instruction fetch stage, we can just make PC write signal 0. Understand? And then also ID stage is the same. So this is the instruction fetch and ID pipeline register. And then also this if ID write equal 0, then what will happen? This is not updated by this value. So if we just see this previous slide, then you can find that at clock cycle 3, load is here, and is here, right? And is here, and aura is here. And then if this pipeline register is not updated, then what will happen? Y is still here. And then, so that means that the end is still here. Okay. And then if ID write control signal becomes 1, then OR will propagate to the ID stage. Okay. To understand this behavior. Okay. So this So I explained how to store instruction fetch stage and instruction decoding stage. So in order to store instruction fetch stage, we can just make PC write 0, and then in order to store ID stage, we can make IF ID write signal 0. Okay. Okay. So I explained how to store pipelines, and then we need to generate NOP. It's the no operation. Now, how can we generate the NOP? So that means the NOP operation, NOP instruction. So we can just make control signals to EX stage or zeros. Okay. So at the first day of the chapter 4, I explained that, maybe some previous class, I explained that the processor is just the black box, and then processor received the instruction, and then based on this instruction, processor changed the state. So what state is the register file and memory? Okay. And then, as you know, this operation is actually controlled by control signals. So if we want to update the value, the data in the register file, then we can activate the read write control signal. And then also, if we just focus on the memory, and then we can just make the mem write 1. Okay, in order to write the new data to memory. Also, we can, if the branch instruction is executed, then PC will be updated by target of the branch. So, but if the branch control signal is 1. Okay. So if a certain control signal becomes 1, then the PC can be updated by the target of the branch instructions, or the content inside of the register file can be updated, or the data in the data memory can be updated. That means if we make these signals zeros, then this processor will do nothing. And then that's the definition of a NOP. So in order to generate the NOP instruction, then we can just make all control signals zeros. Do you understand? So the load data hazard is detected, then we need to make bubble to the EX stage. And then in order to generate this NOP instruction to the EX stage, then we can just make the all control signals zeros, and then that's it. We don't need to change the RS1, RS2, and RD. Why? It's just input source register number or destination register number. Even though this destination register number has a certain value, and this value will not generate any effect to the Datapath element if the control signals are all zeros. Okay. So now to generate the NOP, then we can just make all control signals zeros. So now we explain when to detect and how to detect, and then what should what to do. Okay, so how to detect, and then when to detect, and then what to do for the load use data hazard. Okay, I hope you can understand easily. Okay, so this is the condition, and then so the pipeline timing is explained, and then how the pipelines work for the load use data hazard. Okay, so try to understand if you do not understand how the load use hazard works. It's also important topic in this course. Okay. And then as I explained, if the load use data hazard happen, then clock cycles can be wasted. The clock cycles are wasted, and then if the clock cycles are wasted, performance is degraded. So at the first class of the pipeline architecture, so I explained that if we just build the end stage of a pipeline processor, then performance of the pipeline processor can be, that means I said can be, not always, so can be n times of single cycle processor. Why? In the single cycle processor, one instruction is complete its own operation within one clock. And then if we just build n stage of pipeline architecture, then we can divide these critical paths of the instruction into n parts. Okay, n parts. So that means we can reduce the clock period of the pipeline processor by the clock period of the single cycle processor divided by n. This is the ideal case, as you know. So for the ideal case, if we just use the n stage pipeline processor, then the expected performance is the n times of a single cycle processor. But because of hazard, so if we just see the single cycle processor, this load use data hazard will not happen. Why? At the end of the clock period, end of the cycle, the result of the alt-type instructions or result of load instructions will be surely written back to the register file in the single cycle processor. And then the next instruction can read this written back data from the register file. So actually this load use data hazard will not happen in the single cycle processor. But the pipeline processor, as you know, the data hazard can happen. That means the cycles are wasted by data hazard. So the performance will be less than, so this is the ideal performance of the pipeline processor, that is n times of a single cycle processor. But actually the performance is less than lower than the n times of a single cycle processor. Okay. Because cycles can be wasted due to hazard. Okay. And then I already explained the compiler technology that can improve the performance of a pipeline architecture. So by adjusting the order of instructions, and then by inserting unrelated instruction between the dependent instruction pair, then we can improve the performance of this code. So I already explained here. So you can find that compared to this code, this code will consume less number of cycles. That means the performance can be improved. Okay, so this is the end of the data hazard, and then I hope every student can understand how to handle data hazard inside of a single cycle processor. So this is very important topic. And then before moving on the next topic, so let's take the quiz. So actually I prepared this quiz for the previous class, but in the previous class we are so busy, so we did not take this quiz. Okay. So we will move on to the next topic in 3 minutes. So actually, one of the issues of this online class is that I cannot see students' faces. So, so actually, and usually this pipeline processor is a tricky part of this computer architecture course. And but because I cannot see a student's faces, then I don't know if they understand or not. So that's the problem. Okay. I believe every student understands how pipeline works, then especially how the data hazards are handled in the pipeline processor. Then, okay, and then the next topic of the pipeline processor is the control hazard. So what is the control hazard? So in the previous topic, we learned about how to handle data hazard. So data hazard means that clock cycles are wasted due to data dependencies. And then control hazard means that the same clock cycles are wasted and due to what? Due to control instructions. So what are control instructions? Branches or jump instructions. Okay, right, right. Thank you. So, and then let's see why clock cycles are wasted by branch instructions, like control instructions. And then this is the example. So as you can see, this is the BQ, and then after these BQ instructions, there are several instructions such as AND or add instructions. And then this number represents PC, the program counter value. So, and then this is the 40, 44, and then 48, 52. And then as you know, the gap between the PC of the current instruction and the PC of the very next instruction is 4 for the RISC-V ISA, because the size of a single instruction of RISC-V is 4 bytes. Okay, so that means if the size of the instruction is different, then this PC value of the next instruction can be also different. Okay, but no, for the RISC-V instruction, the size of a single instruction is 4, so that's why the next instruction is 44, 48, 52. So if you see the PC values of the next instruction, then we can know, oh, this instruction is the next instruction, very next instruction of the current instruction here. Then is 44. If the PC is 40, and then if the next PC is the 44, then that means that this is the very next instruction. Okay. And then let us assume that the target of this branch instruction is 72. So this example shows when the condition of this branch instruction is true. Okay. So condition is true. So we need to jump to the target of the branch instruction. It's a 72. Then let's see how this branch instruction is executed in the pipeline processor. At clock cycle number 1, branch instruction is in the instruction fetch. And then clock cycle number 2, BQ is in the ID stage. And then the next instruction. The next instruction and the instruction is in the instruction fetch stage. Why? The branch instruction is in the ID stage, and then we do not know the result of branch instruction. Why? Branch instruction is in the ID stage. When the branch instruction, the result of the branch instruction is reserved. So if you see that this PQ, X1, and X0, so we need to check the data from 2 registers. Okay. And then this comparison is performed by ALU. So until these operands are calculated by ALU, then we don't know the result of this branch instruction. Okay, and then the ALU is located inside of EX stage. So we don't know yet. So in the next cycle, the clock cycle number 3, branches in the EX stage and then end is in the ID stage here, and then the OR is in the instruction fetch stage. So when the branch instruction is in the EX stage, then this ALU receives the data from X1 and X0, and then performs the what operation? Solve operation. So just compare. So X1 minus X0. So this is actually 0. Okay, and then check the zeros. Okay, but you know the ALU is also combinational logic, and then combinational logic has delay. Okay, and then why ALU is located in the EX stage? So delay of this ALU maybe it's less than the period of the one clock signal. So, but this is the clock period, but we may expect that the delay of this ALU is less than clock period, but maybe the result will be generated around here, the late part of the clock period. So what's the problem? Then if this result is generated at the later part of the clock period, then if this, in order to apply the result of the branch instruction, then several data paths also located in some data paths until the program counter. So in the EX stage, we just performs the solve operation, and then the zero is generated, the zero signal. So you know, if you see the ALU, you can find the zero output, but this zero will be generated at the later part of the clock period. Okay, so around here. So we cannot use this signal directly because we need the additional data path elements to update this result to the until program counter. Okay, so in the PQ is in the EX stage, and is ID, or is or instruction is in the instruction fetch stage. And then in the EX stage, this zero value is delivered to some multiplexers, and then multiplexer signals, and then this multiplexer select the target of the branch instruction, and then because this signal is delivered to the input of the program counter. So which timing? At clock cycle 4, this zero signal is delivered to the some data path element here, and then when this zero signal is delivered, the next PC is, so you need to focus on the next PC. So next PC becomes the 72. Okay, so it's a 72. It's a next PC. Okay, so if we just see the PC register, this is D, this is Q, then you can see this is the next PC, this is the current PC. So this is the 72 when at clock cycle 4. So what does that mean? The current PC value is still 52. So add instruction is in the instruction fetch or is in the at ID stage, and the instruction is in the EX stage, then BQ is in the memory stage. Okay. Understand? And then at this time, the next PC becomes the 72. Here, 72. And then what is the current PC? Current PC is 52. So, in the next cycle, the clock cycle number 5, at the rising edge of the clock, so here, this is the rising edge. So at the rising edge of the clock, this 72 is updated to the current PC. And then if the current PC is updated, it becomes a 72. And then in the instruction fetch stage, the current PC is 72. So that means the instruction pointed by PC number 72. So you need to know the instruction pointed by PC value 72. What is which instruction? This load instruction is fetched from the instruction memory. So here, so the load is here. So in this example, the condition of the BQ is true, but when this result is updated or result is reflected to the pipeline process, when at clock cycle number 5. So if we just see so at clock cycle number 1, the branch is firstly fetched, but the result of this branch instruction, so that is the target instruction. So actually, the next instruction of this branch instruction should be this instruction, because the PC is 72. But because this result is reserved very late, when the branch instruction is CC5, so that means clock cycle number 5, the very next instruction of the branches, that is the target of the branch instruction, is fetched to this pipeline processor. When clock cycle number 5, then what will happen? So if you see this pipeline stage, so BQ is the write back stage, and the instruction is in the memory, Bora is here, and is in the ID stage. And then the load instruction, that is the target of the branch instruction, is in the instruction fetch stage. What's wrong? What is the issue for this case? So issue is that this is the AND instruction is the wrong instruction, the incorrect instruction. OR instruction is also incorrect. AND instruction is also incorrect. So instead of add or and or add instructions, we need to execute load instruction, because that is the target of the branch instruction. But because the result of the branch instruction is reserved very late, the pipeline processor has also this and or add instructions. What should we do? We need to cancel and or add instructions. So that means and or add instructions become nope. So and becomes nope, or becomes nope, add becomes nope. So that means it's bubble. Those are bubble. So if you see just this clock cycle number 5 in the stages of a pipeline, you can find that there are 3 bubbles, and then branch instruction is in the write back stage, and then the target of the branch instruction is in the instruction fetch stage. So there are 3 bubbles. That means 3 cycles are wasted because of branch instruction. Then because of true branch, actually, if the condition is true, so if this result of this branch instruction is not true, that means false, then the next instructions are executed. So that means we don't need to waste clock cycles. And what's the problem? The result of this branch instruction is true. So that means the condition is true. And then because this condition of the branch instruction is true, then we need to cancel these 3 instructions in the pipeline the processor. And then this target of the branch instruction is updated to this process, the batch to this processor very late. Okay, so we need to cancel 3 stages of pipeline processor in this case, which means 3 cycles are wasted because of true branch. Okay, true branch instruction. If the result of the branch instruction is true, so cycles are wasted, and that means it's a hazard. But what's the reason of the hazard? It's the branch instruction. It's the control instructions. So this hazard is called control hazard. Okay. So the problem is that when the branch condition is true, if the branch if a branch is true, that means we need to waste 3 cycles. That is the problem. The performance will be degraded. Then how can we avoid this case? Then actually the textbook shows how to reduce these wasted cycles. Okay, so one possible way is that, as you can see, this data comparator is added the very next of the outputs of a register file. So this hardware is added. Okay. Then what is the benefit? So benefit means that, so and then actually this is the register file, and then register file is it's a relatively fast. So it's a very long journey to the previous slide. But if you see some delays for the where is it? So if you just see this delay, so it's not a ridiculous number. So actually it's a little bit reasonable number. So actually the delay of the register file is 100 picosecond. So this is because the register file is very fast. Okay. So usually, and then, you know, because it will take around the 100 picosecond. It's not real number, but if we just compare the delay of the ALU, or if we just compare with the delay of the data memory, this access latency for register file is relatively low. So that means that the register file is faster than other data path element. So that means if the RS1 or RS2 is given to this register file, the data will be out in very short delay of the register file, like 100 picosecond. So if we just see the clock period like this, then we can say that the output of the register file will be generated around this time. Okay, so it's the earlier part of the clock period. So that means if we can add very simple data comparator here, and then this data comparator just compares two data out from the register file, and then if these two data are equivalent, then it generates the one. And then actually this hardware is also very simple. We can use exclusive OR gate for this comparator. Okay, why? If we just see the input and output of the exclusive OR here, 0, 0, what is the number? 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. So actually the meaning of the exclusive OR means that if the two inputs are identical, then the output of the exclusive OR becomes 0. And then if the two inputs are different, then the output of the exclusive OR becomes 1. So if we can use the bitwise exclusive OR hardware for this comparator, and then if we just detect the 1 for this bitwise exclusive OR, then we can easily implement the data comparator. Okay, so that means that the data comparison can be done around here of the clock period of ID staging. So in the previous configuration, the previous pipeline processor, then the result of the branch instruction, like this 0, this 0 is delivered to the muxes of this PC update path in memory stage. Okay, but in the enhanced pipeline architecture, this comparator is added at the output of the register file. So that means that this 0 signal can be generated in the ID stage. Then what's the benefit? When the BQ is in the ID stage, then the 0 is reserved around here. So within the pipeline, within the clock period, and then the next PC becomes the target of the branch when the branch instruction is in the ID stage. So that means that the next PC is set around here, but before the next rising edge of the clock. Okay, so next PC is reserved at this point. So that means this is the very next instruction. Branch instruction is in the ID stage. Now after 1 clock, BQ is in the EX stage, and then the target of the branch instruction is in the instruction fetch stage. And then this is the wrong instruction. This end instruction becomes the nope, so bubble. So what's the benefit? The benefit of this hardware is that when the branch instruction is true, then we just waste one clock. Why? The result of the branch instruction is resolved earlier. Okay. So if we compare this clock cycle diagram, this new hardware will waste only one clock when the branch instruction is true. So we can reduce the control hazard by branch instruction. Okay, this is the enhanced processor design. Okay. Okay. So I stop here, and then in the next class I will briefly explain about the branch prediction and how exceptions are handled in the pipeline process. Okay. Do you have any questions? Okay. Thank you for your attention, and then see you in the next class.